that advertised car also has high miles, then that's evidence against buying it. Maybe it's in a color you like, or it's only had one owner and has all the options you want, or something like that. There is other information in deciding whether or not that price is justifiable. But holding everything else equal, that car is priced above what we would expect, so we may not purchase it, because we're expecting to pay $12,300. So what's the residual here? How different are those two prices? How different is this observed advertised price against what we predicted? So we're going to take the y minus the y hat. So the 13,300 minus the 12,367.85. Oops. 13,300 minus the 12,000. And you should get something about $1,000, $932.15. Okay, so that's the residual. How different is that advertised car from what we expect? So it's above the line, the residual is positive, and maybe that's not worth purchasing. Okay, so what's the predicted advertised or average cost of a car that's 15 years old? Hopefully, you've recognized that 15 is pretty old. In fact, it's outside the scope of the data. Okay, so the correct answer would be something like, we cannot make this prediction as 15 is outside the scope of the data. Remember, the scope was 1 to 13. Well, what if you didn't know that? That's okay. You can just plug that into the line also. So you don't have to keep rewriting the equation. I'm just doing it for illustration. So now x is going to be 15. So we do this multiplication, and then we subtract it from the 14,000. So 959.05 times 15, and then 14,285.95 minus that answer. So you get a negative 99.8. So what does this mean? Our best fit line here is saying if someone is advertising that they have a 15-year-old used Toyota Corolla, they will give you $100 to come and take it. The cost that we expect to pay is negative $100. So that means the person would give us money. Clearly, that doesn't make sense. And this is the danger of using your best fit line outside the scope of the data. It may not make sense. And you have to remember, a straight line goes forever in both ways. Forever up, forever down. So you can plug whatever values of x you want into that best fit line, and it will spit out a y hat. You have to make sure that it makes sense to do that operation. So you have to make sure that you're working where you have data, that you're staying within the scope. Okay, a couple more, well, one more. How much would we expect to pay for a 9-year-old car? And would we purchase one that's $5,000 and compute its residual? So same thing. X is 9, plug that into the best fit equation. So 14,285.95 minus 959.05 times 9. So you get $5,000 $654.50. Should you purchase a 9-year-old car advertised for $5,000? Maybe. Seems like it could be a good deal. That's below what we would expect. Again, in the real world, you would account for other variables. But again, what this is saying is everything held equal. Would you pay $5,000 if you expect to pay $5,600? Yeah, that seems like a good deal. It's below what we expect. So what that means is our residual should be negative. So we start with the observed data point, 5,000, and we subtract our prediction, 5,654.5, and you'll get something like negative 654.5. I don't know why I use my calculator. I could have done that in my head. Oh well. Okay, so that's how you use the best fit line. This allows us these predictions, let you fill in the gaps. You don't need data everywhere. You can use the data nearby to make pretty good inferences where you have gaps. That makes this method pretty powerful. You can do a lot of cool stuff with regression. Now we'll turn our attention to that second table on the output. So this thing with the parameter estimates, and we'll go through it briefly and try to figure out what all it's telling us. So the first column are the parameters of our line. So it's saying, okay, this row will tell us all about the intercept parameter, so that's A. And this will tell us all about the slope parameter, that's B. So the second column, these are the estimates. So it's telling you that using the least squares method, the intercept value is estimated to be that 14,285. So that's where this value in the best fit line equation comes from. The slope, negative 959. So this is just a more explicit way of seeing what the values are. They're still in the best fit line, but it's maybe a little more easy to glean them from this table. There's a standard error, so the variability associated with this estimate. So what you can do is you can create confidence intervals for these parameters. We won't do it, but those are possible. So we'll ignore the standard error table for now. It doesn't mean it's not useful, it just means we're not going to use it. So we'll look at the end. So there's a column called the alternative. So this is an alternative hypothesis. And both of these, it's saying the alternative hypothesis is that something is not 0. What could those be? What hypotheses are being tested in each case? So there's a hypothesis for the intercept and there's a hypothesis for the slope. So we'll talk about those. There's a degrees of freedom. We don't really need this. There's a t-stat. So this is your test statistic from a student's t-distribution. Maybe kind of useful, but we won't really use it directly. So what we'll care about is the p-value. So really what we want are these 4 columns. Those are the ones that have the information we want. So for whatever these hypothesis tests are, we'll hash that out just shortly. We have the p-values for those tests. So they're pretty small. Commonly what statistical software will do is kind of cut off the p-values. So all that this is saying is it's something less than 0.0001. In other words, it's really, really small. It won't tell you the exact value. It just tells you it's pretty small. Okay, so let's think about those hypotheses. So the hypotheses for the intercept and slope are just like hypotheses for a mean or a proportion. There's a parameter that we want to know. We have some hypothesized value, and then we have a claim for what we might think is true. So for the intercept, there's going to be an HO and an HA. And what we know is, from that table, is that the alternative is not 0. So this tells us that the null is 0. So now we have to think back to the purpose of hypothesis tests, and that's to infer the value of a parameter. So if we're doing a hypothesis test about an intercept, then this means we're testing what the true intercept could be. So we denoted that alpha. So the hypothesis test for the intercept is saying, let's assume that the true intercept of all the data of that true best fit line is 0, meaning it goes through the origin, 0, 0. And the alternative is just, it's not 0. Okay. Kind of straightforward. So basically it's telling you, where does your line start? Where does it cross the y-axis? Now this this hypothesis isn't overly useful. Okay? And in most data, it doesn't make sense for the intercept to be 0. Say these data. Does it make sense if a car is 0 years old that its y-intercept will be 0? That its advertised price will be 0? You'll pay $0 for a brand new car. No, that makes no sense. If you really wanted to test the intercept, you would have to change this to something other than 0. This is just the default. So what we saw was our p-value was less than 0.0001. So for any alpha you choose, 0.05, 0.1, 0.01, your p-value will be less than that. So for these data, they support the alternative. They support that the true intercept is not 0, as we would expect. It doesn't make sense to pay $0 for a brand new car. So that's what the hypothesis is. At least in what I've worked on, I never really look at the hypothesis test for an intercept. And I typically don't care what the intercept is. Another thing to think about is 0 even in the scope of your data? Is x equals 0 in the scope? And many times it's not. So this default hypothesis test is outside the scope, so it doesn't mean anything anyways. The one we really care about is the hypothesis test for slope. So it's set up the same way. The table told us that the alternative is not 0, so that means the null is 0, and we're testing the true slope, which we called beta. Okay, so the null hypothesis is saying, let's assume that for this true line, the true slope is 0. Well, what does that mean? What does a line with 0 slope look like? It's a flat line. It doesn't rise, it doesn't fall, it doesn't go up or down. We would say that this means there's no association. So that's really what the null hypothesis is about. Is there an association between your two variables? Or sorry, that's what this hypothesis test is all about. Is there an association? And it tests that by looking at just the slope. So if the slope is 0, you have a flat line, nothing's happening. There's no association. So the alternative is that the slope is not 0. Could go up, could go down, we don't know, but it's just not flat. So in other words, the alternative hypothesis is saying that there is an association. Okay. So, do the data here support that a linear association exists between the age and the advertised price of these used Toyota Corollas? So we're testing this hypothesis test. So what we saw, again, was that our p-value was less than 0.0001. And we weren't given, or we haven't decided upon, a level of significance yet. But that's okay, because it doesn't matter. No matter what alpha you choose, say, even if you were wanting to be very stringent and picked 1%, that's a small alpha. In this case, the p-value is less than alpha. So this means we would support HA. So our conclusion would be something like, at the 1% level of significance, or whatever level you chose, 5%, 10%, doesn't really matter. And we discussed